Let's look at this problem. In this case, we have a beam, this L-shaped beam that is supported here at point A by a pin support and at point C, a rocker support. So we need to be able to identify the support reactions associated with these two. I'm going to draw a free body diagram separately, but just a brief sketch. We will have AX and AY here, two support reactions associated with the pin, and only a CY here, one support reaction associated with a rocker or roller or contact surface. Um, Again, if the supports are different, you need to be able to identify the corresponding support reactions accordingly. But in this case, very standard pin support and roller support. Sorry, rocker support. Um, Here we have two kinds of distributed loads. This right here is a uniform distributed load. Therefore, we can replace that by one concentrated force at the center, and that will equal to 100 Newton per meter times 5 meter. That will be your 500 Newton right here. And here we have a linearly distributed load, and the shape is a trapezoid shape. So for that, we're going to break that into two pieces. We will have a triangular shape, and that can be replaced by a concentrated force of 200 Newton per meter minus 100 Newton per meter, because this portion right here, this height is only 100 Newton per meter, multiplied by the 6 meter divided by 2, that will give you the area of the triangle. So 100 multiplied by 6 divided by 2, that will be 300 here. And lastly, we have another rectangular shape, this right here, that's replaced by a concentrated force here in the middle, and that will give you 100 times 6 meters, 600 meter right here, 600 Newton right here. So with that said, we can now draw our actual free body diagram. Okay. So right here we will have our unknown CY, our unknown AX and AY. Okay. Here we have a force that is 500 Newton right here in the center, that is 2.5 meter away from point A. And then we have a 300 Newton right here. Okay, and this location is going to be 1/3 from the base. That's going to be 2 meter. And then we will have a 600 Newton right here, and the location is going to be 3 meter. Okay, so that completes the free body diagram. This is a 2D rigid body equilibrium problem. Therefore, we can write three scalar equations. We can solve for three unknowns, and we do have three unknowns, AX, AY, and CY. So we will write our three equations: resultant force along the x direction. According to convention, right direction is positive. Therefore, we have our negative 500 Newton minus AX equals to 0. Sorry, plus AX equals to 0. Resultant force along the y direction by convention, up is positive. So we will have our positive AY minus 300 Newton minus 600 Newton plus CY equals to 0. And then we will have our resultant moment. It's up to you where you want to summarize your moment about. We're going to summarize it about point A. According to convention, counterclockwise is positive. In this case, AX and AY both pass through point A. They don't have moment about point A. The 500 Newton is causing counterclockwise rotational effect, so that's positive. 500 times moment arm of 2.5 meter. And then we have 300 Newton force that is causing clockwise, so negative 300 times the moment arm of 2 meter. And then we will have the 600 Newton times the moment arm of 3 meter. And lastly, don't forget your Cy is causing counterclockwise rotational effect with a moment arm of 6 meter. So that will be your three equations, all set to 0 because of equilibrium. From there, you can solve for your three unknowns. I will probably solve for Cy from the last equation, and then Ax from the first equation. And then with Cy solved from the last equation, plug that into the second equation, you can solve for Ay. So as a result, Ax equals to 500 Newton, Ay equals to 708 Newton, and lastly, your Cy equals to 192 Newton. Okay, and that's the answer.